Hello, I am Yann Stoneman, and this is part 3 of my Study With Me series on the Kafka Streams DSL, domain-specific language. And last time we left off at transform a stream, and let's do just the stateless transformations for this video. I think that'll be plenty of content, so headed over to there. And by the way, I noticed that there's a slightly updated version of the documentation that I'm using today. I noticed a link at the top of the documentation I was using for the last video that said go to this updated version. It looks pretty similar, so I don't think we need to update anything about the last two videos, but I'll use this updated version, I guess number 30 here, just in case. Stateless transformations. Stateless transformations do not require state for processing. Makes sense. And they do not require a state store associated with the stream processor, right? If you don't need state, you don't need a state store. Kafka 0.11 and later allows you to materialize the result from a stateless k-table transformation. A stateless k-table transformation. To me, k-table means state, but I guess you can transform something from a k-table statelessly. This allows the result to be queried through interactive queries. To materialize a k-table, each of the below stateless operations can be augmented with an optional queryable store name argument. Okay, so this heading for the stateless transformations has a lot about k-table, but like this one doesn't apply to k-table. It's k-stream to a branched k-stream. Okay, so there are some transformations that apply to k-tables though that are stateless. So I guess the transformation itself is stateless, even though it's going from a stateful thing, a k-table, which does have a state store. The transformation itself is not stateful. It does not need a state store. So you're going between a k-table and a k-table. Each of these has its own state store. It's named because you got to give a k-table a name when you create it or when you add data to it. And the transformation between these two, though, if you're doing a stateless transformation, does not have a state store. I guess that's probably one thing they're pointing out here. And the word materialize is interesting. I've seen that come up a few times in this documentation. So to materialize a k-table, each of the below stateless operations can be augmented with an optional queryable store name argument. Okay, I guess that means even though it's a stateless operation, you can augment that by putting the output into another k-table, thereby materializing it, making it appear, making a k-table appear. I mean, that's what materialize essentially means, right? Making it appear, creating something. So to create I'm going to just use the word create here to see if it makes more sense. To create a k-table from a stateless transformation, you can add a queryable store name argument, and then the output will be a k-table, right? I think that's because a k-table can be queried with interactive queries. Okay, I think I'm getting somewhere here. Transformation of a called branch. So this is our first stateless transformation is branch. First, what does that look like? K-stream becomes a branched k-stream. And the description is branch or split a k-stream based on the supplied predicates into one or more k-stream instances. Okay. Based on the supplied predicates. Okay, so you got to tell it based on what parameters, what predicates you want it to split the input stream. And based on that, that logic, it'll split it into one or more. Predicates are evaluated in order. A record is placed to one and only one output stream on the first match. Okay, and I think that's kind of what makes it stateless, because as soon as there's a match, it just sends it off to an output stream. It doesn't hold on to that in any way. It just, once it's processed, it goes to an output stream. If the nth predicate evaluates to true, the record is placed to nth stream. Okay, so if you've got, let's say 4 conditions, so to speak, predicates, and the 4th condition evaluates true, I guess if the other ones haven't, the first, the second, and the third predicate were all false, and then the fourth one evaluates to true, then that record goes to the fourth stream. So I guess there are as many potential streams as there are predicates. If the fourth one never evaluates to true ever, I guess there will never ever be that fourth stream. But as long as it evaluates to true once, there will be a fourth stream, or an nth stream. So if a record does not match any predicates, it will be routed to the default branch or dropped if no default branch is created. Okay, let me read that again. If a record does not match any predicates, so you can either send non-matching records to a default branch, or if you don't specify this, like in Java here, you can do .default branch and then specify which branch. Or if you don't specify it, then it just gets dropped. The record gets dropped. Branching is useful, for example, to route records to different downstream topics. So you've got code here for the example, and let's go through that. So we've got kstream string long stream equals. So I guess this is a stream object here, and then this is map. Okay, I guess because branching is kind of a form of mapping, we're taking values from a stream and mapping it to new streams. So that makes sense that it says map here. So branches equals stream.split named as, so we're splitting the stream, that makes sense, named as branch dash. So when I see branch dash, I wonder if that means it'll be like branch dash A. Oh yeah, there we go. Branch dash A. So it seems like we can name a prefix here and it'll add the suffix here based on a predicate. So, okay, it'll add the suffix here actually. The predicate is here. If a key for a record starts with A, so like Apple 5, and if the key is Bugatti and the value is 5, then it says, oh, the key starts with a B. And if it is Volkswagen, then that starts with a V, and that doesn't match A or B, so it goes to the default branch, branched as C. And each one of these, so if it starts with A, the A suffix will be appended to branch dash, and if it starts with B, the B suffix right here will be appended to this. So I guess the kind of the as dot notation here is for naming in this case. Named as branch dash and then branched as A. So the name, that's the kind of core of the naming, and then the branching, that specifies a suffix. Okay, I think I got that part. Okay, first predicate, second predicate, default branch. Okay, so pretty intuitive language here. Kstream branches.get branch-a contains all records whose keys start with A, and B contains all records whose keys start with B. C contains all other records because it's the default branch. And Java 7 example, cf.filter for how to create predicate instances. What's CF short for? The abbreviation CF, short for Latin confer, conferatur, both meaning compare, is used in writing to refer the reader to other material to make a comparison with the topic being discussed. Okay, so as a comparison, filter for how to create predicate instances, or refer to filter for how to create predicate instances. Okay, I'm not sure what this is talking about, but I'll leave that as an open question. Maybe I'll come back to it at another time. Filter is our next stateless transformation, and we've got kstream to kstream and ktable to ktable. And a filter evaluates a Boolean function for each element and retains those for which the function returns true. That makes sense. Filter is pretty common in most programming languages, at least the two I'm most familiar with, JavaScript and Python. And I guess there are more details about kstream filtering and ktable filtering, but we'll leave that for now. Let's just see the examples. The one example they have here. They have a filter that selects or keeps only positive numbers. And this example is written in Java 8++. plus, and this example is probably the same thing, but in 7. Seems like you can be more concise in Java 8 plus than in 7. Oh yeah, because lambda expressions tend to be concise. Looks almost more like Python. All right, anyway, K-stream, string long, only positives. It takes the stream in, applies a filter here with dot notation, and you provide a key and a value. Oh, or it takes the key and the value as an input, and it outputs the value only if it is greater than 0. So only keeping the positives. Oh, okay. No, it doesn't only output the value. It takes the key and the value and outputs the key and the value where the value is greater than 0. And in the Java 7 example, same thing, but a little more language to make that happen. String long, only positives, stream.filter. This part's the same. And then this long part is doing the same thing that this one little part was doing in Java 8 plus. It was creating the condition. The condition is value is greater than 0, but here we have to write new predicate string long override public boolean test. Oh, so you gotta create a little function here. String key, long value, return value is greater than 0. Oof, anyone still using Java 7, I hope you switch to 8 plus soon for the sake of your developers. That does not look fun. Okay, moving on to the next stateless transformation. Inverse filter, K-stream to K-stream, K-table to K-table. All right, so evaluates a Boolean function for each element and drops those for which the function returns true. K-stream details, K-table details. Yep, so we'll skip those details and just look at the code here. So this is the same as filter, but it just drops the ones for where it's not true. I mean, in some ways, you never need an inverse filter. You can just always make the condition flipped instead of flipping this part. You could have filter. We're achieving the same result as in the example above with the filter, but we're doing it in a different way by using the filter not. So in the first example, we were explicitly keeping the positives, and here we're dropping the negatives. Same result, slightly different approach. An inverse filter that discards any negative numbers or 0. Java 8 plus example using lambda expressions. Yeah, so same as the above example. Java 8 plus is more concise than Java 7. And then the next stateless transformation is FlatMap. So you take a K-stream and you get out a K-stream. By the way, let's keep in mind here that branch is from a K-stream to a branched K-stream, so stream to stream. Filter, an inverse filter, can be stream to stream or table to table. And FlatMap, again, same as with branching, is stream to stream. But unlike branch, where you could have multiple output streams, with a FlatMap, you only have a single output stream, or 0. Oh, no, it's still one stream as an output, but a single record could produce 0, 1, or more records in that single output stream. You can modify the record keys and values, including their types. Okay. Marks the stream for data repartitioning. Okay, so within that output stream, the data is going to be differently partitioned, probably, depending on how you map it. Applying a grouping or a join after FlatMap will result in repartitioning of the records. If possible, use FlatMap values instead, which will not cause data repartitioning, right? If possible, use means it's more efficient, probably, more performant to use FlatMap values to avoid the data repartitioning. Oh, okay, so applying a grouping or a join after FlatMap. That repartitioning that you got to watch out for with FlatMap only happens if you apply a grouping or a join after doing that FlatMap function. So let's see if they do that in this example. We've got the FlatMap here. Is there a grouping after that? I see that there's a result, and to the result we're putting to uppercase and to lowercase. And what does that do? So let's read the comment here about what that's trying to achieve. Here we generate 2 output records for each input record. Okay, so we have an input stream And the output stream is going to have twice as many records. We also change the key and value types. So as an example, we have an integer here, or no, 345L. What type is that? And then hello. So this looks like some sort of hex, but hex doesn't have L. Anyway, it's not in quotes. Oh, I guess that's a long in Java. A long type takes 64 bits of memory. And okay, so we have a long and a string, which is mentioned here, and that's the original input stream. And that outputs a string and an integer. A string and an integer is what the transformed stream looks like. But it doesn't only output a string and an integer, it does that 2 times. So it takes the input value and makes that the key and makes it uppercase, and then kind of randomly, we don't know why it chooses 1000, but it chooses 1000 for each single value. And then for the second in the pair here, I guess in the linked list to be more specific, it makes that input value be a lowercase output key, and then 9000 as the value. So with this function here, for creating a transformed stream, every single record in the output stream will be a linked list, and it'll always have 1000, 9000, because those are hard-coded here. There's no logic to that. It's just hard-coded, 1000 and 9000. And whatever the input value will be the output key, is how that works in this example. I guess that's just to show that you can generate more than one output record, and you can change the type, and you can change the order. A lot you can do. And it's still stateless because it just takes one record, does a transformation, and puts it in the output. It doesn't have to add things together or keep track of anything. As soon as it's done, it can forget about that record. Map, I guess, is related to key value mapper in Java 7. All right, let's do one more, and then we'll probably split up this stateless transformations into a separate video. So FlatMap, values only, k-stream to k-stream. Takes one record and produces 0, 1, or more records while retaining the key of the original record. You can modify the record values and the value type. So that sounds like it's exactly the same as FlatMap so far, right? Takes one record and produces 0, 1, or more records. It's the same, but this time we're retaining the key. We're only changing the values. We can modify the record values and the value type. We can't touch the keys. The function itself looks different too. FlatMap versus FlatMap values. And FlatMap values is preferable to FlatMap because it will not cause data repartitioning. However, you cannot modify the key or key type like FlatMap does. So whenever you don't have to change the keys in a FlatMap, use FlatMap values. It's more efficient. Split a sentence into words is the example here in the code. So kstream byte array and string, that's the input stream, I guess, format, and that's the input stream is called sentences. And again, FlatMap is a k-stream to a k-stream, nothing to do with tables. And then k-stream, I was just thinking, why couldn't you have a FlatMap for a table? You can have a filter for a table, right? Which makes sense because you've got all these values in a table, and I guess you would essentially be dropping certain rows if they don't match the filter value. And you can have a branching based on a predicate, right? But that is also only stream. Okay. I guess FlatMap can actually create several records with the same key because it can output more than one record into a single stream as an output. And when you've got more than one record for a single key, that's just interpreted as an update in a table. So kind of useless. So that's maybe one reason that FlatMap can't be done with tables. Comment below if you have additional ideas. And let's see, kstream byte string words equals sentences dot FlatMap values. Looks like they're using a lambda here. Okay, so this is probably like Java 8+, and then I think I'm understanding this comment now. They're saying if you want to do this in Java 7, you got to use value mapper instance. Okay. So sentence.flatmap values, it takes the value. Notice that it doesn't need the key as an input because it doesn't even touch it. So no need to even input that into the function. It's not part of the logic. So takes the value as an input in flatmap values and outputs arrays as list value dot split by white space, one or more white space, or 0 or more. I'd have to look that up, the regex there. But just splitting by white space and putting for each sentence the words as an array. Cool. Yeah, I guess that makes sense. You still have the same byte array at the beginning, but then instead of a single string, you have a string of words. I'm confused why the type is still string here instead of like array of strings, but I'm not that strong on Java. I'm more of a JavaScript and Python guy, but essentially the logic is a sentence here to an array of strings here. Cool. So let's pick up next time with for each, because this is already becoming a long video on the stateless transformations. So just to review where we're at here in the Streams DSL documentation, we've gone through the first few sections, and now we're probably 30% of the way through stateless transformations. Hope that helped. Leave a comment below if you have any questions, and make sure to subscribe so you get the next video in this series. And thanks for watching.